So now let us try to understand the constructional features of our synchronous machine. Okay, so we know that every electrical machine has these components: stator, rotor, air gap and shaft, and bearings, etc., etc. Okay, so we know that there is a stationary member, that is stator, and rotatory member, that is rotor, and air gap is between stator and rotor. Okay, this air gap is between stator and rotor, we already know that, and it should be as minimum as possible to reduce the reluctance between stator and rotor flex. Okay, so this is one is stator, another is rotor, third one air gap, and fourth one is shaft, and there will be other additional parts, bearings, yoke, etc., etc. Okay, and there will be ventilation, radial ventilation or axial ventilation to dissipate the heat, okay, from the machine. Okay, so these are the physical parts that we can see, but here there is another additional components that our machine possesses. Their excitation winding or field winding, another is armature winding. Okay, we know that our excitation or field winding will produce our working flex. Working flex will be produced by our excitation winding, and armature winding carries load current. So we need two windings for operation of a rotating machine, right? One is exciting field winding or armature winding. Okay, sorry, one is exciting or field winding, another is armature winding. Okay, exciting or field winding is to produce working flex, and armature winding is to carry load current. So what are these load current and working flex? Okay, so what is a load current? The current in winding that varies as machine is loaded. That means as the load on the machine increases, the current in that winding will also increase. That means our load current is proportional to loading on the machine. I can say IL is load current here. Okay, so then what is exciting current here? The current that produces working flex in the machine. Okay, this produces only working flex and it doesn't vary with the load. Okay, this is exciting current, that is we make it IM is magnetizing current or working current. It can be also called exciting current, field current or magnetizing current. Okay, these magnetizing current only produce our working flex in the machine. Okay, it won't change with respect to load on the machine, but our load current will change with respect to load on the machine. Okay, as the load increases, our load current will increase. Okay, so this is about the parts, main components in our electrical machine. Okay, stator, rotor, air gap, shaft, bearing, yoke, and radial and axial ventilations. And there are two types of windings: exciting and field winding to produce the flex, and armature winding to carry the load current. Okay, what is the load current? The current in a winding that varies with respect to load is load current, and exciting or field or magnetizing current is current that produces only working flex and it doesn't vary with the load. Okay, this is about components. Now let us start from stator so that we can understand the machine. So let us try to understand the stator construction. Okay, this is similar to stator of our 3-phase induction motor, which is having a hollow cylindrical shape and inner periphery is slotted. Okay, this is a hollow cylindrical structure. Okay, it is cylindrical actually. Okay, it is sideways, that is so that you can see that it is oval shape, but it is a cylindrical shape having inner periphery slotted. Okay, these are the slots made on the inner periphery of our cylindrical stator. Okay, so these slots are open type slots. Okay, you already know that the types of slots are type of slots used for our synchronous machine are open type slots. Okay, why it is open type? Because keeping of the already made winding is easy. Keeping of farmer winding is easy on open type slots. Okay, and there is less leakage flux in the open type slots. Okay, which is useful for our armature reaction, okay, that we will be discussing further. Okay, the types of slots used for our synchronous machine are open type slots. Okay, and these types of slots are made on the inner periphery to accommodate armature winding. Okay, we know that armature winding is mostly placed on the stator in our synchronous machine. Why it is placed on our stator winding is explained in induction machines also. So there are so many advantages keeping our stator winding on the stator, because it is more economical to have armature winding on the stator and field winding on the rotor. Okay, because we will be supplying only DC excitation to our rotor. If we keep armature winding on the stator, we don't need to have 3 slip rings on the rotor, we only need 2 slip rings to supply DC plus and minus. Okay, if we keep armature winding on the rotor, we have to keep 3 slip rings. Okay, R by B phase sequences. For 3-phase AC winding we need R by B, right? So we will be needing 3 slip rings on the rotor if we keep armature winding on the rotor. That's why, and slip rings causes some mechanical losses and there is loss of efficiency. That's why our armature winding is placed on stator instead of rotor. This is one advantage. And efficient cooling. We can cool the stationary armature winding more efficiently, and it will permit us to construct large synchronous machines around 100 megawatt, 1000 megawatts. Okay, so as it is, our armature winding is placed on the stator of our synchronous machine, we can have efficient cooling methods to dissipate the heat induced in the armature winding, so that we can have large amount of armature winding that will increase the capacity of the machine in the order of 1000 megawatts. Okay, we can create a machine having 1000 megawatts of rating if we keep armature winding on the stator. So we keep our field winding on the rotor and armature winding on the stator. Armature winding is bulky and large compared to our rotor winding, that is field winding. So keeping field winding, which is very less weight compared to armature winding, will reduce the weight of the rotor, that will reduce the centrifugal force and inertia of the rotor. While it is rotating, there will be less centrifugal forces on the periphery of the rotor because it is having less weighted field winding. Okay, so that is also one advantage. Keeping field winding on the rotor will reduce the inertia of the machine and it will reduce the centrifugal forces while running. Okay, so that is, there are so many advantages of keeping our armature winding on the stator. I will explain in the next step. Okay, so let us try to understand what is there on the stator. Okay, and the stator is made up of our cold rolled non-oriented steel. Okay, this is important. Okay, our transformer core is made of CRGO steel, which is cold rolled grain oriented steel. But in case of our synchronous machines, we use cold rolled non-oriented steel with 3% of silicon. So why do we need to add silicon to our core material? Okay, in order to reduce eddy currents, we need to reduce the conductivity of our material. That means by increasing the percentage of silicon, we can increase the resistivity of the core material. That will reduce the conductivity of the material. That means the electric current flow in the stator core will be less. That means the eddy currents flow will be reduced. That reduces the eddy current loss. If you increase the resistivity, current flow will reduce, which are eddy currents. The loss due to eddy currents will also be reduced. Okay, so by adding silicon, we are reducing the eddy currents. Okay, and core is laminated. You already know that lamination means small parts of core will be made and then it will be staggered together to form like this. Very small, in the order of 3 mm to 5 mm. Okay, these are the laminations of the core and they will be bunched together to form one core. This lamination is to reduce the eddy current losses. Okay, eddy current loss will be reduced by laminating the stator core. These are the small laminations having 3 mm to 5 mm. So this is the range of laminations, 3 mm to 5 mm. So the small laminations will be bunched together to form one stator core and that will reduce our eddy currents. Okay, so this is about our synchronous machine stator, which is having number of slots made on the inner periphery of the stator to accommodate our 3-phase armature winding. Okay, so why do we need to accommodate armature winding on the stator only? Why not it can be mounted on the rotor? So let us see what is the advantage of keeping armature winding on the stator. Okay, so now let us try to understand advantage of keeping armature winding on our stator. Okay, so first point is it is more economical. So it is more economical to keep our armature winding on the stator. So why? Let us try to understand considering a problem. Okay, why it is economical to keep our stator winding or armature winding on the stator. Okay, so let us consider a 3-phase star connected 200 volts 200 MVA 11 kV synchronous machine. Okay, this is current power S, this is my line to line voltage 11 kV. Okay, this is the rating of the machine 200 MVA and 11 kV is the supply voltage rating. So now let us try to find our line current in the machine. That can be found by apparent power S by root 3 times line to line current, line to line voltage. This is line current expression. Okay, by substituting values 200 by root 3 times our line voltage, we get the line current value in the order of 10,500 amps. So this is the order of current in our synchronous generator. We can see the order of currents is around 10,500 amps. Have you ever seen this much of current so far? No. So that's why these are very large machines. Okay, you can see from that. Okay, now let us find out the phase voltage to be VL by root 3, 11 by root 3 equal to 6.35 kV. So why I am finding these values? Okay, if I want to keep our armature winding on our rotor, now let us say what is happening. So rotor has to have 3 slip rings for 3 types of phases R, Y, B, and hence it is star connected. We will need extra winding, extra slip ring for star connection in the winding, that is 4th slip ring. So we will need 4 slip rings here. 3 are for 3 phases and 1 is for star connected terminal. Okay, so the line current is in the order of 10,500 amperes. So in order to handle this much of current, our slip rings must be made to handle 10,500 ampere of current. 10.5 kilo ampere of current will flow through these slip rings. So these slip rings should be made. So you need to have high grade slip rings and high grade insulation, and you have to brought out one extra winding, which is a star connected winding, and you need to keep one extra slip ring for that, and you need to ground it through a resistor, and the grounding material should be required. Okay, so this overall setup will increase the cost of the machine. Now let us try to understand, if I keep our field winding on the rotor, what is happening? Okay, earlier I keep our armature winding on the stator. So this is what happening if I keep armature winding. Now let us try to understand, if I keep our field winding on the rotor. So if I keep armature winding on the stator, so this is the setup I have to make. That is increasing the cost of the machine. Now let us try to keep our field winding on the rotor. Now let us see what is happening. Okay, so initially I was keeping 4 slip rings to have 3 phases and 1 extra star connected point. So for a field winding I will be needing only 2 slip rings, right, for plus and minus. So because it is a DC supply, I will be needing only 2 slip rings here. So cost of extra 2 slip rings is reduced now. Okay, the cost of extra 2 slip rings in case of stator armature winding placing on the rotor is reduced by 2 slip rings. Okay, and you can supply your rotor with 2 slip rings plus and minus. And let us consider a field winding of 1 megawatt rating with a 500 volts. Okay, so the current will be around 2000 amps compared to 10,500 amps. 2000 amps is very less. It is 5 times less compared to 10,500 amps. Okay, the less current will flow through the slip ring, so less grade quantity, low grade slip rings are sufficient to carry this 2000 amps, and each slip ring should be insulated from shaft for a 500 volts. So instead of 6.35 kilovolts, we have to insulate our slip ring from shaft for a 500 volts. That means the voltage stress on the insulation material is very less. That means we can use low grade insulation. We can use low grade slip rings if you keep field winding on the rotor, and low grade insulation, so that will reduce the cost of the machine. Okay, so this is why it is economical to keep field winding on the rotor and armature winding on the stator, so that the overall cost of the machine will reduce. Okay, that's why it is more economical. Okay, keeping our armature winding on the stator is more economical compared to keeping our armature winding on the rotor. So that was about more economical. Okay, keeping our armature winding on the stator is more economical compared to keeping our armature winding on the rotor. Okay, now let us see, it is more efficient. Why it is more efficient? We have seen that there are only 2 slip rings needed on the shaft to connect DC supply to our field winding. Okay, if you keep field winding on the rotor and armature winding on the stator, so these slip rings generally have losses. Okay, there is contact loss, or I can say mechanical loss too while rotation. Okay, if you have 4 slip rings, the loss due to 4 slip ring is more compared to 2 slip rings, right? So if you have placed your armature winding on the rotor, there will be 4 slip rings, right? So the loss due to 4 slip rings is more compared to loss due to these 2 slip rings. Okay, these 2 slip rings are slip rings for a field winding. Okay, so loss due to 4 slip rings is more compared to loss due to 2 slip rings. That's why we are reducing the losses by keeping only 2 slip rings on the rotor shaft, so that we can reduce the overall loss. If loss is reduced, the efficiency of the machine will increase. So this is one point. Okay, now let us consider this one more important point, that is better insulation is possible while we keep our armature winding on the stator. So what is insulation? So we have slots on the stators, right? So we are going to keep our winding on the stator slots. So here the slots and conductors should be insulated. Okay, to avoid short circuit, a slot and a conductor carrying current should be insulated, so that our machine will free from short circuit operation. Okay, so this insulation is better if you keep our armature winding on the stator, and this insulation, if insulation is better, you can build a machine of order 33 kV. Okay, the insulation material is placed based on the voltage stress applied on the insulation material. So the more is the voltage, the more will be the stress on the insulation material. So if you keep armature winding on the stator, which is stationary, so it is very useful to keep armature winding on the stator, because we can use better insulation from conductor to slot, so that we can increase the rating of the machine to 33 kilovolts. Okay, insulation is having the dependent of our voltage stress on the conductor. Okay, the more is the voltage, the more high grade insulation should be used. Okay, and it is possible if you keep our armature winding stationary. While it is rotating, the insulation may get loosened because of the centrifugal force of the rotor while it is rotating to handle this much of current. Okay, so that means the material used for slip ring should be very high grade, and it should be very costly to handle that much of current. And why I have calculated phase voltage means, here these slip rings will have this phase voltage, each slip ring will have phase voltage of 6.3 kilovolts, and that voltage should be insulated from this shaft material. Okay, each slip ring should be insulated from shaft, so that there will be no short circuit between slip ring and rotor shaft. So more high grade insulation is required. High grade insulation is required between our slip ring and shaft. High grade insulation is required, and high grade material are required for our slip rings. High grade material to carry 10,500 ampere of current. Okay, so having high grade material of insulation and high grade material of slip rings, the cost of the machine will increase. Okay, so and you have to brought out the star point between between the windings and ground it to through a resistor. Okay, there should be a grounding metal and that should be grounded using a resistor, and this will increase the cost of the machine. It may loosen or get away from these slots, okay, or misplaced from these slots, so that will cause short circuit from conductor to our slot, that will damage the machine. That's why keeping in state armature winding on the stator is more useful in case of insulation, so that we can provide better insulation from conductor to slot, so that we can increase the voltage rating of the machine in order to 33 kV. So this is the order of voltage that is generating in our power stations, 11 kV or 33 kV. Nowadays it is 33 kV. Initially it was 11 kV. Of course there are 11 kV generators also available, but most of them are 33 kV now. Okay, then generating voltage is in the order of 11 kV and 33 kV because of this insulation constraint. Okay, if you want to increase the generated voltage, you have to keep very high grade insulation, that will increase the cost of the material, and it is not possible to keep high grade insulation because the cost is more, and this is the limitation of generated voltage for a generating plant. That's why 33 kV is the only generating power that we obtain till now. Okay, because it has an insulation constraint. Okay, if you want to increase the rating of the machine to 66 kV, you need to have more insulation between conductor and slot, that is conductor and stator core. It is not possible. Okay, the more economical generation is 11 kV or 33 kV. Okay, without any insulation problem. So that was about more output. This is fourth advantage of keeping our armature winding on the stator, because we keep armature winding on the stator and field winding on the rotor. Okay, we know that the weight of armature winding is more compared to weight of field winding. Okay, if you keep less weighted winding on the rotor, we can rotate it faster so that we can obtain more output. Okay, our power output of synchronous machine is proportional to speed actually. Okay, so more is the speed, more power will be obtained. So when more speed will be obtained, when there is less weight of rotor is there. Okay, if the weight of the rotor is less, we can rotate it faster so that we can obtain more power. So that is about more power output. Okay, now the fifth thing is lesser rotor inertia. So we already seen that our weight of the field winding on the rotor is less, so that there is less inertia on the rotor. Okay, rotor will have less inertia. J is inertia constant. Okay, less inertia on the rotor, so that we can rotate it faster. Okay, that is less inertia concept. And the last final important thing is more armature tooth strength. That means we are going to keep our armature winding on the stator slots, right? So if you want to generate more power, you can have more winding on the stator slots, so that you can have deeper slots, so that you can keep more windings. You can get more output power. Okay, that's why more armature tooth strength is possible if you keep armature winding on the stator. Okay, so these are the advantages of keeping our armature winding on the stator instead of rotor. Okay, so these are the advantages. Now let us see construction of rotor. Air gap is non-uniform, that is minimum air gap between, go here you can see this is minimum air gap between rotor and stator, and here it is air gap is increasing from pole center to pole core. Okay, that is non-uniform distribution. Here from pole center to stator there is less air gap between stator and rotor, and air gap is increasing while we are going away from the pole center. So that's why it is non-uniform air gap, and that causes non-uniform flux distribution. Non-uniform flux distribution. Okay, non-uniform air gap will cause non-uniform flux distribution. Okay, now flux distribution in silent pole machine can be improved by shaping the silent pole such a way that having minimum air gap along the pole center and increasing towards pole ends. Okay, here this non-uniform flux distribution can be overcome by a type of core that is chamfered core. Chamfered means having minimum air gap at the pole center and its air gap should be increased while it is away from the pole center. This non-uniform air gap is causing non-uniform flux distribution. Okay, in order to eliminate this non-uniform flux distribution, our salient pole should be made in a way that there should be minimum air gap at the pole core, center of the pole core, and here the salient pole should be made in such a way that at the core center that there should be minimum air gap, and air gap should be increased towards the pole's end. This is pole end, this is pole center. Okay, the type of salient pole where there is a minimum air gap at the pole center and maximum air gap at the pole end is called chamfered poles. Okay, these are called chamfered poles. Okay, chamfered poles. Okay, if you can make this salient pole having minimum air gap at the pole center and having maximum air gap at the pole end, you can somehow improve this flux distribution to uniform. Okay, that is done by chamfered poles here. Okay, normal poles will also be there. Normal poles will be like this. Okay, this is non-salient pole, which is a normal pole, but this is a chamfered pole. Okay, chamfered poles are preferred to improve the flux distribution. Okay, and the speed range of our salient pole machine is in the order of 50 to 1000 rpm. We know that our synchronous machine rotates at synchronous speed, that is 120 into f by p, where f is the frequency of armature current and p is the number of field poles. Okay, so for a 50 rpm machine, what is the number of poles? That is 12 for a 50 Hz frequency. For a 50 Hz frequency, to have 50 rpm, you will need 12 poles. 12 number of poles will be needed on the rotor core. Okay, for a 1000 rpm, you will need 6 poles on the rotor. Okay, so this is the speed range of our machine, and that's why this is a order of 50 to 1000 rpm. Okay, these are called low speed alternators. Our silent pole machines are called low speed alternators because they are having just 50 to 1000 rpm range. Okay, anything can be possible between these two. Okay, and the power developed is proportional to volume of the core. Okay, the power developed in the rotor is proportional to volume of the core. The volume of the core is diameter square into length square. D is diameter here, D is diameter, and L is length of the core, length of rotor. Okay, these are rotors, right? Diameter of the rotor and length of the rotor. For our silent pole, diameter is more compared to length of the machine. Okay, here the diameter is more, here the diameter is more compared to length. Okay, this is length. Length is less compared to diameter. Okay, diameter of silent pole is large compared to length. Okay, so diameter is in the order of 5 times length. That means length to diameter ratio is around 0.2. Okay, that's why these are called low speed alternators, because they are having low speeds of rotation, and they are the suitable prime movers to rotate these rotors, because this is a generator. Okay, we need to rotate the rotor, right? You already know that. So we rotate our rotor using a prime mover. The suitable prime movers for our silent pole rotor are hydro and diesel prime movers. These are the prime movers for our silent pole rotor. Okay, hydro means using water you have to rotate the silent pole rotor, and using a diesel power. Okay, so our silent machines, our silent rotor is used in a hydroelectric power plant. Mostly the best application of our silent pole is hydroelectric power plant, because there the speeds of the motor, the speeds of the machine are very less. Okay, and they can also be used in diesel power plant. Okay, this is about silent pole rotor. Okay, silent pole rotor has a shape like this, and the field winding is placed on the pole core, and it generates non-uniform flux distribution to reduce or to improve that non-uniform flux distribution to uniform distribution, because our non-uniform flux distribution is the main reason for production of harmonics. Okay, so if flux density waveform is non-sinusoidal, then induced EMF also non-sinusoidal. So the non-sinusoidal induced EMF will consist of harmonics. Therefore, to reduce these harmonics, we use a type of poles. They are called chamfered poles, where the air gap is minimum at the pole center and air gap will be increasing towards the pole end. Okay, at the pole center the air gap between stator and rotor is less, and it will increase towards pole end. Okay, that they are called chamfered poles, and they are used for our silent machine. Okay, the speed range of our silent machine is around 50 to 1000 rpm, So the number of poles will be like this. For 50 rpm it is 12, for 1000 rpm it is 6, because it is a synchronous speed machine. Okay, so the silent pole machines are called low speed machines, and the power generated is proportional to volume of the core. The volume of core is diameter square into length. Okay, d square into L. Diameter is more compared to length for a silent pole machine. The diameter to length ratio is like this, and length to diameter ratio is around 0.2. And the suitable prime movers to rotate our silent pole rotor is hydro and diesel prime movers. Okay, most used application is in hydroelectric power plant. So this is about silent pole rotor. Now let us see what is cylindrical pole rotor. Now this is second type of our synchronous machines rotor, that is cylindrical rotor. It can also be called as round rotor. Okay, it is a round rotor or non-salient rotor. It can also be called as non-salient because it is opposite to salient. That means salient is projecting outwards. So cylindrical machine has no projected poles. Okay, mostly they will have two number of poles. Okay, so this is the type of structure for a rotor of cylindrical type. Okay, now let us see the points here. So 2/3 of rotor is slotted and 1/3 is left for pole formation. Here this is 2/3 of rotor periphery which is slotted, and 1/3 of rotor periphery is open for pole formation. Okay, and air gap is uniform here. Air gap means the gap between stator and rotor. Let us consider the red color one is a stator. Okay, this is the red color one, and you can see the air gap is same all over the rotor periphery, and that means the gap between stator and rotor is same all over the periphery of the rotor. That means uniform air gap will be there, which will result in uniform flux distribution, that is sinusoidal flux distribution is possible. In non-salient poles we are not having this sinusoidal flux distribution due to the poles which are projected outwards. So we can use our chamfered poles to have improved flux distribution in silent pole machine. Okay, but here there is no problem with non-uniform distribution of flux because the uniform air gap will cause our flux distribution sinusoidal. Okay, and the type of material used for the rotor is a solid steel. It is not laminated, it is solid, made up of nickel, chromium and molybdenum for increased mechanical strength. Okay, so why they use solid steel means there is a problem of hunting in case of our synchronous machines. Okay, so to reduce the problem of hunting, we will use solid steel that will act as eddy current damping, that I will explain later. Okay, in the case of damping and hunting, so eddy current damping is possible for a solid steel if you use solid steel for a rotor. Okay, that is to eliminate the hunting. Okay, that will explain later. Okay, the speed range of our cylindrical type rotor is in order of 1500 rpm to 3000 rpm. For silent rotor it was 50 to 1000 rpm. So that's why they are low speed alternators. It is now for a cylindrical type rotor, the speed range is between 1500 to 3000 rpm. That means they are called high speed alternators. The cylindrical rotor type alternators are called high speed alternators, having the speed of 1500 to 3000 rpm. So for a 1500 there will be 4 poles for a 50 Hz, and for a 3000 there will be 2 poles for a 50 Hz supply. So this is the most commonly used configuration of our cylindrical machines. Okay, for a 2 pole you will have 3000 rpm of rotation. Okay, so this is the most useful used configuration, that is having 2 poles on the rotor and speed of the rotor is 3000 rpm, which is rotated by a turbine. Okay, so the length of the material here, the length of the core is more compared to diameter. In case of silent pole the diameter was more compared to length, but in case of our cylindrical type the length is more because our cylindrical motor will have high speeds. Okay, the speed of the machine is very high. Okay, if you have more diameter there will be more centrifugal forces. Okay, that's why we will use less diameter and more length core materials in case of our cylindrical type. Okay, that's why they can handle this much of speeds. If the diameter is more, the centrifugal force acting on the rotor which is having high diameter also more. Okay, that will disturb the rotation of the machine, the machine will vibrate. That's why we decrease the diameter and increase the length so that we can handle this much of speeds. So it doesn't have any silent poles. That's why it is non-silent poles. Okay, here this is the construction of our silent rotor. Okay, which is having a field winding will be distributed in slots. Okay, here you can see that this is a cylindrical type rotor. Okay, 2/3 of our rotor periphery is slotted. Okay, arrow in the whole rotor periphery, 2/3 times of whole rotor periphery is slotted. Okay, slots are made on the 2/3 of periphery, and 1/3, this is 1/3 of the rotor periphery is open to produce our poles. Okay, see, that means 2/3 of the rotor slots are made on the rotor and 1/3 will be left to form the poles, field poles. Okay, so the placement of the winding is distributed all over the periphery of the rotor. That means here this will be the distribution of winding. Okay, the field winding is distributed all over the rotor periphery. Okay, here you can see the number of slots are distributed all over the periphery of the rotor. Okay, so like this. These are overhangs. These parts are called overhangs. The conductor, the real conductor that experiences the magnetic, that produces a useful flux. In case of our magnetic field is this one. Okay, this is useful conductor. Okay, here you have like this. Okay, I hope you understand. Okay, here the field winding is distributed all over the rotor periphery, and 2/3 of the rotor periphery is slotted to accommodate the field winding, and 1/3 is left open to form the poles. Okay, most of the cases cylindrical machines will have in the order of poles. The structure of the silent pole is like this, which is having more diameter compared to length. Okay, so more diameter means the rotor, if rotor has more diameter, the stator will also have more diameter, so that you can accommodate more number of slots on the stator. Okay, so in silent pole machines we are having more diameter and less length, because the speeds of the machines, the silent pole, are very less, in order of 52,000 rpm. That's why we don't need to bother about centrifugal forces, because the speeds are less. So we will be having high amount of more diameter and less length. That means, so for a silent pole you will be having more diameter and less length. So for a more diameter of the rotor, you will need more diameter of stator also. Okay, so diameter of the rotor increases means our stator diameter also increases, so that you can have more space to accommodate slots on the stator of our silent pole machine, so that you can have less amount of length. Okay, that's why this is the structure of silent pole, which is having more diameter and less length. But in case of cylindrical, you will be having more length compared to diameter. Length to diameter ratio is in the order of 5:7. Okay, the length is more compared to diameter, which is 5 to 7 times of diameter. Okay, the length is more in case of cylindrical. Okay, so here the suitable prime movers are, this is important, this is the suitable prime movers to rotate our cylindrical type rotor are steam turbines. Okay, steam means which is produced in thermal power plant, and gas turbines. So these alternators are used in thermal power plants, gas power plants, and important one is nuclear power plant. So the type of rotor used for nuclear power plant is cylindrical type rotor. Okay, this is mostly used compared to silent pole, because thermal power plants are more generating, almost 70% of power generation is due to thermal power plants only. So that's why cylindrical rotors are more useful compared to silent pole. Silent pole is used in hydroelectric power plants and diesel power plants, but cylindrical type rotor is used in thermal power plant, gas power plant, and important one is nuclear power plant. So this is about constructional details of our cylindrical machine. In the next class we will be discussing about working principle. Okay, thank you.